Thank you very much for waiting, ladies and gentlemen. Now we'll begin session 1, the impact of climate change on food supply and demand. We have Dr. Shiratori Sakiko, project leader of JIRCAS, to moderate. So over to you, madam. Could we have a warm applause for Dr. Shiratori?
Thank you very much. I am Shiratori from JIRCAS. I will serve as the moderator for this part of the program. This is session 1, and we will look at the yield impact of climate change on world food supply and demand. First of all, Dr. Iizumi Toshichika, Senior Research Fellow, Impact Assessment and Adaptation Group, Division of Climate Change Adaptation Research, Institute for Agro-Environmental Sciences of NARO. He has released many models, original crop models based on his analysis in leading journals. The title is Yield Forecast of Major Crops in the World Under Climate Change. Thank you for the introduction. My name is Iizumi. The main screen is the Japanese and the sub-screen is English. So if you could look at the left-hand side screen, please. My presentation, basically I will talk about two aspects. Why are we trying to project climate change impacts onto the future global crop production? This is about the motivation. And how we project into the future. What is important is the crop model and the input to future scenarios. There are many different scenarios. For example, CO2 emission and concentration, or climate, or agricultural R&D, and many others. So first of all, our motivation. Why are we working on this? Whether it be climate change or global warming, the Earth is becoming warmer all over the world. Last year, 2023, it was the record hottest year. This year, 2024, at a very high probability, it is going to see a record high. Based on 2015, going back to the temperature before 2015 is rare. Every year, it is renewing a record high in the last few years. So these are the observed climate change, and already across the world there are observed impacts onto the crop production, and the yield rise is pressed down. Working Group 2, according to Assessment Report 6, it says that overall agricultural productivity has increased, but climate change has slowed this growth over the past 50 years globally. And this is medium confidence. The left graph indicates what IPCC is stating in the assessment report. Using wheat as one example, the global average yield before 1990, it grew 4.2% per annum. But in the more recent years, the growth per annum is down to 1.7%. Same with rice. So far, from the past to today, yield has risen. However, in order to respond to increasing demand, the yield has to continue to rise. However, because of climate change, where the growth is slowing, which is our concern, and therefore R&D adaptations have to be implemented in order to compensate for the negative climate change. And if the climate change is positive, then we need to amplify such positive impact. How to project into the future? Crop model is used. Eco-physiological processes-based computer simulation program is what we use. So in the computer, we try to grow the crop. What we input is the temperature, precipitation, solar radiation, humidity, or soil condition, CO2, the timing of sowing, how much irrigation or fertilizer, these kind of input will be used into the crop model. The land of the world is 50 kilometer grid divided, and for different locations on the earth, on a daily basis, the crop will be cultivated. So not only the yield, but what is the timing of the harvest, the leaf area, amount of biomass, evaporation, transpiration, these information can be collected. It is rather a heavy computer model, and therefore high-performance computer, or a supercomputer as it is known, this is the infrastructure that will be required for this kind of analysis. And the crop model we use is Sigma. What can Sigma do? A daily estimate of the crop growth can be simulated, and we can reproduce the observed differences between the varieties, meaning earlier past varieties and the recent varieties. For example, Sudan, East Africa, irrigated wheat is the example. On the left-hand side is the observed. On the right-hand side is the reproduced by model. In Sudan, when the temperature is high, the trend is that the yield goes down. But for the older purple variety, compared to that more recent variety, which is shown in blue, even if the temperature rises by 10%, the yield increases. So there are differences between the varieties, and the model can identify these characteristics. Under the Sigma model, it is a growth tracking on a daily basis. For example, if the leaves, after sowing, how the leaves increase, how the biomass will increase, and from the maturity, and then we can see the yield as a result. The scenario to be input into the crop model is equally important, and it has to be prepared. For example, the emission scenario, and then the atmospheric CO2 concentration will be determined. Then climate scenarios will be decided within the crop model. As the climate condition changes, the agronomy will also be adjusted. This is part of adaptation to the climate change. So the sowing date will be changed in the model, or the more calorific requirement may increase during the growth period. And the socio-economic scenario will produce the agricultural R&D scenario, amount of fertilizer input or variety improvement. These percentages will be determined. These scenarios will be input, and the yield per grid will be calculated. And then afterwards, by multiplying with the harvest area, then the average for country or region can be calculated, and then this would be input into the food demand supply model. More specific about the scenario, under the sixth assessment report of IPCC, there are 5 emission scenarios. We have looked at the low, medium, and high scenarios. The gray part is the middle of the century. So high emission, medium emission, and low emission. These are the scenarios. And the name of the scenario, it says SSP. This is a bit too technical. So in the middle of the century, compared to pre-industrialization, increase 1.7, 2.0, 2.4, 2.4, degrees rise. The speakers later, I think, will be using non-technical languages like that. And working group 1, the climate model, there are 38 used, and out of that, 3 of the models that have high reproducibility of recent temperature increases are shown here. 2 from Japan, 1 from Germany, and the color shows different emission, and 3 lines in the same color. And this is the difference of the different climate model. The temperature. This is the emission. With a high emission, then there will be a larger rise. This is common to all model, but the change of the precipitation, the results are mixed. And the spatial pattern is like this. So the average of the 3 GCM in the middle of the century compared to pre-industrialization, and looking at the difference on the polar regions, there is a larger temperature rise, which is common to all emission scenario. The precipitation change is quite similar, but in the Mediterranean region or Brazil, Amazon area, aridification, less rain is significant. And next is the agricultural technology scenario. Nitrogen, fertilizer. For different countries, the average fertilizer input can be explained mostly by per capita GDP and per capita agricultural land area. In a given country, the amount of fertilizer and the amount, there is the 2000 global data, and by combining that for different crop, different country, this is amount of fertilizer, and the left is the estimate, and the vertical line is the reported. And we can reproduce the past fertilizer application, and the color difference is based on different report. That indicates the different symbols. To apply into the future, this is the finding. The colored part is the middle of the century, where it is the prediction period. Even if the fertilizer is increased, there is a limit to how the yield can rise, and therefore the fertilizer increase also has to be stopped at some level. Per hectare, 200 kilo is the upper limit. For the soybean, these are a pulse, and they can fix nitrogen. So compared to cereal, not much fertilizer required, and therefore you can see that the fertilizer remains low. So the sensitivity are also factored in. And next is out of the agricultural scenario, the R&D part per country. Per year, IFPRI produces the spending data. In order to explain this, GDP and the share of agriculture within the GDP and the sector average expenditure on R&D are used as the indicators to create the model. So in this way, we are able to reproduce the R&D expenditure, and the annual R&D expenditure is calculated from 1960. So from R&D until actual commercialization, there is the time lag, and then there will be a certain percentage of the technology that will become obsolete. And after the integration, the graph is indicated on the lower part. Within the crop model, the agricultural knowledge stock, depending on the knowledge stock, the share of improved variety will be determined. And this is the result of the yield simulation. So MRI, this is the Japanese Meteorological Agency model, and the emission scenario, low, medium, high emission, and one example is maize. Around North America, relatively, if it is colored, that is a high yield area, and because of temperature increase, it shrinks. We can see in North America and Brazil. Under this crop model, the global gridded crop model, in the area where it is not cultivated, if the crop is cultivated, the result can be simulated. Therefore, in taiga, in Siberia, it is colored because even if it is not cultivated in reality, it is simulation. Back in 2010, where was the maize actually harvested? And if those maps are overlaid, then, for example, in areas where there is actual harvest, then the average yield per country can be calculated. And for different income group, it will be organized. Some characteristics in low-income country, where there is a big room for further additional high yield increase, and therefore the yield is expected to rise. But by the end of this century, the more the temperature rises, the yield increase will be limited, and ultimately the yield will go down. But we are looking at mid-century, and that trend is not that strong. But for the middle of the century, the trend estimated is similar. And this is for maize, rice, and wheat. And the crop model itself, the yearly yield is calculated. So the yield per annum changes, but this is the average of the 10 years. So the gradient is not that large. The graphs are flat. And 3 climate models are used, and for the 3 scenarios we simply use the average, and therefore the graphs are quite flat. And this is the middle of the century. So for different income level, different emission scenarios, in the case of maize, there is a clear trend. Whatever the income group, the temperature rise. If there is more temperature rise, then the yield will go down. In the low-income country, there is big room for additional tools and technology, and therefore, for all of the crop, there is a bigger increase in the yield compared to higher income countries. And there are mixed impacts of temperature rise. In the case of maize, when the temperature rises much, the yield does go down. But the more the temperature rises, for some of the crop, the yield could actually increase rather than decrease. And one reason might be in the case of wheat. In the high-income country, in terms of latitude, they are higher latitude countries quite often, which means lower temperature was the restriction. But with warmer temperature, in the case of the wheat, the yield would rise in high-income, high-latitude countries. In the case of maize, when temperature rises, this is very vulnerable because the CO2 impact is lower than other crops, and therefore the CO2 concentration, if that rises, the CO2 fixation, photosynthesis will rise, but with the C3 or the C4 type, the CO2 fixation level will be different, and for maize, that effect is lower. And the estimate, this is based on one model of sigma, and if we use a different model, then the yield expectation will also change. It was mentioned earlier by earlier speakers, and I am one of the co-author, but 12 crop models are used in this graph, and I introduced the sigma model. It is shown in the red letter, and for maize and the wheat, very pessimistic, and rice and the wheat, the maize and the soybean very pessimistic, and the rice and the wheat is an average estimate. National Institute of Environmental Studies, there is another crop model incorporated here, and for maize and the soybean it is close to average, and for the wheat and the rice they have a very pessimistic outlook. So when the model is different, it could be as different as this.
Conclusions and points to be heeded. As just showed, with projected slowdown of yield growth among warming is prominent for maize. With regard to rice and wheat, there are both positive and negative impacts. A future increase in yield technology and geographical changes depending on the rise in temperature, the results differ. The yield projections serve and as I'll be introducing by the other speakers, they serve as an input to the food demand-supply model. As for limitations, the uncertainty in project yield changes associated with use of different crop model, and that is substantial. This is just based on one crop model. And in the front lines, multiple crop models are being, a use of multiple crop models are being proposed. And what I showed, the results was a 2010 a harvest area, which was maintained fixed. But the suitable area for cultivation changes. So when you consider the change in area, uncertainty grows. And the crop model sigma, which we use this time, is such that R&D expenditure differs with regard to the social scenario, but the future food prices, it's not dependent on future food prices. It's not dynamic. So that's the limitation in the present method. And also, this is another important point. The scenario that we are dealing with, the agricultural technology scenario, in countries where the yield is already high, an ultra increase in yield technology has not been considered. The reason being that it's difficult to envisage a future scenario with this. We're taking the present high yield technology permeating to developing countries. That's the technology scenario that we have used this time. That is all. Thank you.
Thank you, Dr. Iizumi. This was the introduction of the estimated yield according to Sigma crop model developed by himself and members. Thank you very much.